Hello, my name is Levi Plies, and I'm coming to you from Las Vegas, Nevada. I am a distance student at the North Carolina State University. I'm currently enrolled in Dr. Buckner's MAE ECE 535 course. And as my demonstration, I'm going to do current carrying wires and the magnetic interactions between wires and the magnetic field generated by single wires. Thank you. The demonstration. So first I'm going to walk you through what we've constructed here to show this. Here are our current carrying wires that we're going to use for the demonstration. This is the TIG welder. It's a Mailer Synchrowave 200 TIG welder. We're going to use it on the 200 amp setting. We're going to use it in a DC voltage, and it's going to have 0 pulse, so that way we'll have a solid steady draw out of the welder. That way we'll still have AC current through our wires, but at least it'll be a solid current. It won't be fluctuating due to pulse cycles or bringing the welder up and down. In order to measure the current, went out and got one of these clamp meters. Kind of interesting, a lot of electro principles going on in here. So we're going to use this to measure current as we're performing the welding operation. And I've done several tests before this, and noticed that we get pretty much the same number each time, as long as the settings in the welder remain the same and the same distance from the welding tip to the tool to the work remains about the same. The current stays pretty steady. In order to visualize the magnetic field, kind of put together a little ad hoc device. Essentially, it's 5 small compasses purchased on the internet, and then they're all just glued to a 1/2 inch piece of plywood with a notch in it, so we can slide it around the wire and the wire or wires in this case to view the magnetic field. Okay, so for this portion of the demo, we're going to demonstrate the magnetic field around the current carrying wire. Now, in order to get to a position in the garage that didn't have a existing magnetic field, either due to the welder itself or apparently the table that I uses, it's been magnetized. I've climbed about 6-7 feet up in the air, maybe probably 8. But up here, all of the compasses appear to generally align in a northward direction, which is this direction. Now when you see we apply the current, you'll watch the needles move. And I kind of tap the compass just to excite them. They seem to take a little help in order to start realigning, but now there you go. At steady state, you'll see all of the needles in a circular pattern around the current carrying wire. Okay, so now we're going to get to the portion where we're actually going to measure the current through the wires and then observe the interactions through the wires. So we're going to use the torch, and we're going to put the working material back behind the board so that it doesn't interfere with the light you see here. Using our amp clamp around the wire at a static state without the machine under any load, I'm seeing a 1.6 amp draw. Okay, let's fire it up. And then we immediately jump up to 55 amps of draw. Pretty steady. That was a lot of sparks. Okay, and now let's see what that 55 amps traveling in both directions, that effect on the wires. Just get into a relaxed state here. And here we go. You can see immediately they jump apart together, jump apart under load again, no load, load. Through our 2 demonstrations, we were able to demonstrate first that there was a magnetic field generated by the current carrying wire. It augmented all of the compass needles in the direction of the current, or direction of the magnetic field. In the second demonstration, we were able to show how that magnetic field that's induced actually affects a second current carrying wire in proximity to, and in our case in opposite directions of the current, so they created repulsive force.